alpha and beta. Hence what? If you had a common divisor, a common right divisor, right? You could say, if I define rho, right, equal alpha minus mu beta. In other words, if I take alpha minus some multiple of beta, right? If I take and define, look at this row, this is a definition. Wow, when Forrest is excited, he's really excited. I don't think I've ever heard him talk that way. In his most heated comments in all the department meetings I've been in the last 7 years, it's about the volume, if that. He does not care. He is a model for projecting, I don't care. I love the way I love his demeanor. It's amazing. It's not something I can muster. Anyway, okay, so this is, sorry here, alpha, the gamma delta minus mu beta epsilon delta, right? And you can see what you can do. You can just factor these guys out, right? And you've got gamma minus mu beta epsilon delta. So what do we just find out?
I don't think the beta should be there, because beta is epsilon delta. So alpha minus mu beta is equal to...
Oh yeah. Oh yeah, why is that there? That's just not right. So it's just supposed to be mu, because the epsilon delta is the beta, right? Oh, then I should underline like that. My underlining ignorance. Let's see here. So that's beta. Beta is this. And then I'm supposed to fix this over here. Fixed? Fixed, right? Okay, so now what we see then is that if you take a difference of common right divisors, well, I mean, this is a particular kind of linear combination. The reason this is interesting to us is this is how we deform the remainder, right? When we're doing the division algorithm, we take alpha, we subtract a multiple of the dividing number beta, right? And that's how we define the remainder. Is it working, Cameron?
Mm-hmm.
Okay. Thanks. And so what this shows then is that if I start with, if I'm thinking about alpha divided by beta, right? And I want to think about that being equal to what, like, mu plus what? Rho over beta, basically, right? Which, of course, we trade for the statement that alpha is equal to mu beta plus rho. And so then we define, our rho was so defined as to make that, happen. But you can see that if you had a common divisor for the number which is divided in the dividing number, it then follows that that right divisor is likewise a right divisor for the remainder term, right? But this is exactly what the Euclidean algorithm is logically based on, right? We start with a pair, and then, so you start with what? You go alpha, beta, right? And then your next step in Euclidean algorithm would be what? Beta, and then the remainder, right? And so what this shows is that if delta is a common divisor here, guess what? Delta is still a common divisor over here, right? And then what? And then you can just keep going, right? And then, so it makes sense to say where this terminates is the GCD, what we'll call, language. You could talk about left divisors, and it wouldn't necessarily be the same. I'll just say that, okay? But this is the right GCD of, hey, wait a minute, we're missing somebody.
Walter.
Oh, no.
Caitlin.
They'll come back, right? What?
Giles.
Probably not. Oh, man.
Somebody else. Giles. Sean. That guy. Giles. Walter. No,
That's Walter.
That's Walter.
Walter, Giles, Sean, and
I didn't see it.
There's
Well, since we're missing 4 people.
So I have a video.
Oh, we do a video. But that records the badness of this lecture also. It's a two-way disorder. Oh, okay, so, and I think you can see though, also, if you just build, if you go backwards on this, right? Or you could develop the lemma like was developed in the earlier part of the notes. As long as you're careful not to commute things in the wrong way, you can essentially follow the same arguments, at least as much as the arguments were built on divisibility. You're like, well, how do you know this sequence of things terminates? Well, the other thing was for the dividing, for the division algorithm here, not the Euclidean algorithm, but the division algorithm, the thing that supports this equality, and the fact that you can always do that. One of the things that supported that was, it was paired to the fact that the norm of the remainder was smaller than the norm of the dividing number. So you can't keep going smaller and smaller and smaller. There's only so many Hurwitz integers to work with, so you have to hit like the smallest thing. Not necessarily uniquely, of course, but you can't go on with this forever, so it has to stop somewhere. Because at each step, you're getting to a strictly smaller normed remainder. Okay, so hey, by the way, that's a nice review of why the Euclidean algorithm works, just in our current context. So there's of course a theorem. Sorry. That if alpha and beta are Hurwitz integers, right? Then there exists mu and nu in the Hurwitz integers, such that what? Oh man. Right, this is annoying, isn't it? The right GCD of alpha beta is equal to what? Well, mu alpha plus mu beta. Of course, we called that what? In our previous context.
Bézout's theorem.
Yeah, that's Bézout's theorem, or Bézout's identity. Still true here, just from these calculations, essentially. You just collect things together and identify the coefficients. And of course, once you have that, that gives you the prime divisor property, right? What's the prime divisor property here? It's actually, I don't know if it gets us the full prime divisor property. Honestly, I'm not sure about that. It turns out for the proofs that follow, we don't need something quite so technical, like it's enough to have the prime divisor property just for an ordinary real prime. So like here, the difference in what I'm about to say here versus what I said in the Gaussian integers or in previous context is that I never made the stipulation that P was a real prime in those ones. Like before I just said, suppose P is a Gaussian prime, or suppose P is a prime in the Eisenstein integers, or one of those things. I mean, but now I'm supposing P is a real prime, which means it's also a what? It's really real. I mean, that means it's an integer, right? This thing. And if P divides alpha beta for some alpha and beta in the Hurwitz integers, right, then P divides alpha or P divides beta. Again, this is I would say this is a weakened. Now, here's the thing I don't know, guys, because as I've warned you, I'm no expert on number theory. Probably should just call me Mr. Cook in here and definitely not Dr. Cook. That's always true in physics. I only have a master's in physics, yeah. You should call me doctor there. It's not the right terminology. Again, so the difference was, and when I say I don't know if it can be strengthened either. I don't know if it's true that the prime divisor property holds for Hurwitz primes, yeah, that are not real. I'm not sure. Okay, but we have this. Now we can prove this in much the same way we proved these things before. What was that? What did we do?
Assume that P doesn't divide or alpha.
Yeah, so suppose P does not divide, we can say alpha, one of them, alpha, let's say. Then what? One thing we get is that 1 is equal to the right GCD P and alpha. Now, maybe it wouldn't, I mean, I suppose guys, I mean, thinking about it, I could see that this thing would terminate on something other than 1. Like maybe it would terminate on one of the other more exciting units in the Hurwitz prime, I mean the Hurwitz integers, right? But if you have that, then you can take that and multiply by some other unit, which is the inverse of that unit, to get back to 1. And so you can always create an expression which you can like basically multiply this by some unit to get to the number 1 and make this be 1. If this works out to a unit, you can always multiply what you've done by like a unit to get back to 1. So that's not, there's no loss of generality there. If you thought about this question for the Gaussian integers, you know what I'm talking about. You could have the like 2 Gaussian integers are, I would say 2 Gaussian integers are relatively prime if their GCD works out to like what? Like, oh wait, we had a problem about this, right? 1 minus 1, I or minus I, right? And if you have Bézout's identity for any one of those, you can easily multiply Bézout's identity by something else to get back to a Gaussian integer linear combination equal to the number 1, right? So, and that's essentially what I'm going to use is the Bézout's identity with 1, you know, here, right? So, operatively, it's that we're using. Hence, so I mean, what I'm trying to say is, if you were to like argue with me, well, I don't know that GCD, the right GCD is the number 1. Maybe it's like another unit if you want to think of it that way. Then I would say, well, that's fine, but you can still take Bézout's identity and get this equation. Right? Now that you have that, play with it. The next thing we did at this point in the argument was to multiply that by beta. We did it in the integers. We did it in the Gaussian integers. Now we're doing it in the Hurwitz integers. Okay, so multiply by beta on the right. That matters. Mu p beta plus mu alpha beta. Right? Now, let's see here. Can we notice some things about this expression? Does P divide? Is P a right divisor? Well, let me one more step here. We can rewrite this as mu beta P, right? Because P is a real number. It commutes with everything here, right? You can move that to the right, and then we've got Euler's plus nu alpha beta. Now, I suppose I could trade this beta for what? Like
You can trade alpha beta for P divided.
oh, yeah, that's also true. Okay, so let's do that. So I can trade my alpha beta for like something. Let's say m. P divides alpha beta, which means that alpha beta is equal to m times p, right? For some p, for some n in the Hurwitz integers. Sorry, that way. As p divides alpha beta, we'll assume. Yeah. You're right. I was about to assume that that p divides beta, which would be kind of bad form because that's what we're trying to prove. There's a certain tipping point between staying up late preparing for class and actually giving class. Like there's some kind of like tipping point where you should stop preparing and just go to sleep. This is true for tests too, right? Well, some of you can deny it, but oh, okay. So now that you see it, though, right? What do we have? P divides this guy. P divides that guy. So therefore, what? right? Which is what we set out to prove, right? So if P is real prime and it divides the product, if it doesn't divide one of them, it has to divide the other one, right? So. Is it? I'm not sure that this argument's fair anymore because there's an asymmetry between alpha and beta now. I mean, is this argument logically based on the fact that alpha and beta were logically interchangeable over the integers? Like alpha and beta commute, right? It's not the case anymore. I can't just say alpha beta is equal to beta alpha in the Hurwitz integers. So logically, should I also have to go through the other version, other part of this argument, which would be what? Am I also? I mean, I don't trust sleepy me, so I'm not sure I believe what I'm saying just now. But it's a concern I have. Let's say if P is P. I mean, you can talk me out of it with logic if you want. If P does not divide beta, then what? Then there exists mu and mu such that what? 1 is equal to mu P plus what? Nu beta, right? Oh, so the thing is we have control over which side we multiply the argument by here, right? So this where we multiply it by beta on right, right? I'm sorry, yeah, on the left by beta, right? So if we go through the parallel argument.
It's on the right.
Oh, that one's on the right. Oh, it's on the left. Yeah, you're right. I mean, you're correct. Right. Then this one, I have to multiply it on the left, right? Sorry, you're correct. Multiply it on the left by alpha, right? And that gives me alpha is equal to mu alpha P plus nu. Oh. Alpha nu beta.
I think that you can assume that P divides. Is the rule kind of the same with left divisors though? Like you could redo everything that you did there on the left side of the board with left.
Right.
And it'd be like alpha mu plus beta mu.
Huh. Yeah, I don't know. I feel like he's hiding something here. Tell you what, I'm just going to put a question mark by that one right there. I'm not sure about what to do about that. I mean, I want to believe in your left divisor idea, but should we use left divisors? We talk about the left GCD. Will that fix the problem? I mean, then the alpha and the beta are on the other side of the coefficients, right? I mean, if you were to talk about the left GCD being alpha mu plus beta nu and go through the parallel argument with things on the left. Yeah, but then you would get something about left divisors of alpha and beta, of P being a left divisor of alpha and beta. Oh, but the thing is P is an ordinary prime, so left and right divisors. Oh, I think we just discovered why this theorem doesn't hold in its straight-end form. Because left and right divisors are distinct and non-commutative objects. Like the fact that you can factor a matrix out to the left of a product doesn't mean that you can factor it out to the right of a product. For example, if I have some matrix product like A times let's just say I have ABC, right? it may be the case that I can write this again as ACB, right? And maybe some constant, whatever. But it may not be the case that it's possible, maybe it's not possible to write B times AC times some constant, whatever. We can allow for a plus minus or some constant, generally speaking. So in other words, the fact that B was say a right, I don't know what this is, right divisor, right? Yeah, B was a right divisor of the product ABC. Does not necessarily mean that B is a left divisor of the product ABC. The one special case where it's both is when B commutes. And B is like the P over here. When P is real, it commutes. So if the left divisor is also a right divisor, which is why we get the other half of this argument, which is not in my notes. Now, it's pretty easy to see what kind of, if you've had linear, or if you're about to, whatever. BC, the only way, so some matrices commute, some don't, right? So it could be that B and C are commuting matrices, whereas A and B are not. Okay, that's possible. And well, we saw that we could write quaternions as matrices, right? So if I can give you an argument in terms of matrices, it follows that the same thing is true for quaternions. Okay, I spent too much time on this. Let's get back to Euler stuff, right? Sorry. I hoped we could strengthen it. I should know better by now. I had a student come to me in the first summer I was here, and he wanted to study an analog of what are called, well, you guys know what Gaussian integers are. I don't have to tell you what are called Gaussian integers. You have spent some hours studying Gaussian integers. You know what they are, right? But he just had a number theory course, from Dr. Kessler, and he was really interested in Gaussian integers, and he wanted to see if he could study Gaussian integers in the context of the things I studied in my thesis, which are called supernumbers. Okay, so you're like, well, what's a supernumber? Well, supernumbers are things like this. Well, let's just say Z is an element of supernumbers means that Z has something like this. Z naught plus Zi A to I plus Zij A to Ij, A to I A to J, plus Zijk, A to I, A to J, A to K. And these A's are so-called Grassmann generators. For example, A to 1 times A to 2 is equal to minus A to 2 times A to 1. And this goes on and on. But it's subject to a condition like the norm of Z is equal to the norm of Z naught plus the norm of Zi, we'll sum over that, plus the sum over I and J of these guys. So we work with supernumbers such that this thing is less than infinity. It's essentially the same as working with what are known as L1 sequences. So there's some analysis in there. But the key is that these supernumbers are built over these anti-commuting objects, these so-called Grassmann generators. Okay, so what Coleman wanted to do, he wanted to study, and it's a pretty cool idea now that I think back on it. He wanted to study sort of like Gaussian integers of these things. I don't know why, he just did, So we started trying to look at it. And I never really experienced the joy which is trying to factor in the super. And things I looked at had not required the ideas we go over here in terms of divisors, right? I don't think about divisors in my research. I mean, I study differentiation of functions from supernumbers to supernumbers, whatever. It's awful. It's truly awful. Everything we faced in the quaternions is also waiting for you there. Anytime you try to do like a factorization theorem, in other words, like try to write an object as a product of factors in a non-commutative setting, there's horrible ambiguity which enters. There's a distinction between left and right divisors. And it's so much worse. There's infinitely many units. So like the ambiguity of the prime factorization suffers from that too. It is truly awful. We got nowhere. I mean, I became pretty quickly convinced that it was a hopeless project, but I did learn some new things about supernumbers from doing that. Anyway. So there you go, there's a window inside my thesis. What was I doing? Oh, yes. Here we go. Theorem. Oh, I've relegated it to a proposition. If P is equal to 2n plus 1, then, all right, there exists L and M in Z such that what? P divides 1 plus L squared plus M squared. So this is the sort of like Lagrange's lemma. Right? What was Lagrange's lemma? It was a prime of the form 4n plus 1 divides m squared plus 1, right? We used Wilson's theorem to prove it, remember? It wasn't that hard. Actually, I think that was one of the most fun arguments in chapter 6. It was just like congruence and some kind of sneaky manipulation, but it wasn't really that hard. But this is even easier. Let's see how. So, actually, this argument I'm about to show you, it took me a little. I didn't appreciate it right away. I kind of got to the end of it. I was like, what? So let's see if we can get through it together and not feel that way. So here's the proof. So what he does is he looks at x squared and y squared somewhere in the following list. All right. So if you have x and y in 0, 1, 2, all the way to n. All right. Somewhere in that there list. And with x not equal to y, we do assume x and y are distinct. You can consider x squared plus y, not plus, just you can consider x squared and y squared, right? Certainly you can square those, right? And you can argue then that if x is not equal to y, it also follows that x squared is not equal to y squared mod py. It's not congruent, I should say, to y squared mod p. Since so here's the argument. What we do is we trade x squared, so this is the argument as to y, okay? X squared congruent to y squared mod p. Let's see here, so we could say that implies what? X squared minus y squared congruent to 0 mod p, right? I'm going to get so sick of writing mod p here. I'll deal with it though, but it made me big bucks. All right, let's see here. Let's see here, x minus y, x plus y, p by our old friend algebra. Still useful after all these years. And then what? Well, this means that either what? Either x is congruent to y, or x is congruent to minus y mod p, right? However, what's p? And p is what? It's odd, but it's 2n plus 1, right? I think that's the critical thing here. So if you think about, maybe think about this graphically, right? Here's your 0. Here's n. 1, 2, right? I guess I can afford 3. And so if you just think about x and y, they're somewhere in here, right? I mean, I don't know, x, y, they're somewhere out here. And if you add them, could they be, oh, excuse me, could the, could this minus y is congruent to what? 2n plus 1 minus y, right? If we want to look at, let's suppose that we want to look at the representative that fits on this part of the number line, right? Then I would do this, right? I'd have to add 2n plus 1 minus y. So that would be this guy. Oh, I'm an idiot. Oh, excuse me. So this is y, but this would be not the same thing, right? Let me call this y prime, right? In principle, y prime has to be somewhere in here, right? I'm making it more complicated than it needs to be. Let me stop talking and think for a second. Oh, done. So, yeah. How about this? So 0 is less than or equal to x plus y is less than or equal to what? X is at most what? And y is at most what? And so x plus y is at most 2n. 2n is strictly less than 2n plus 1, okay. Which shows you that this guy, nope, I mean that's not, because, right? I mean, to say x, I mean, again, to go back to the other thing, I mean, maybe I should have just left it x plus y congruent to 0, right? As you can see, x plus y cannot be congruent to 0 here. Oh, why can't you get 0? Why is I have equality here, but why should I really put a strict inequality over here? I'm going to replace it with a green.
Because x is different than y.
X is different than y, exactly. So x and y cannot both be 0 by our assumption. So that's a less than. So in other words, we cannot get to 2n plus 1 or to 0. Those are representatives of the congruence class 0 mod p. What about the other one? X congruent to y. So I argued here my argument was no, it wasn't my argument. Oh, I guess, okay, I said then again, or I should probably say and also 1 is less than the absolute value of x minus y is less than n minus 1. Do you agree with that? Is that ring true to you from our assumption that x and y go from 0 to, or somewhere from 0 to n? And they're not equal, right? If they're equal, we could get 0. That's forbidden. The distance between x and y is, the absolute value of x minus y is the distance between x and y, right? A fact that those of you who are in real analysis are painfully aware of. Let's see here. And then like x minus y can't be n, right? Because why is it less than n minus 1? I feel like why is that? Because if I had y equal to n, and if I had x equal to n and y equal to 0, I have x minus y is n.
It should be equal to 1, too.
Oh, I don't believe that argument. what I'm saying is, what if x and y are on the extremes of this, right? Then they're n apart. Oh, so I could just put an n there, right? I mean, I could make this plus 1.
Shouldn't it also be like 1 is less than or equal to, that's what that would happen as well?
Yeah. Yes. Have somebody here see a reason to resurrect the logic of my notes? Sometimes my notes are more logical than I am, and I regret not following them, but I think this is not such an instance. Okay, so then what? Here's the next argument. So if you think about that, therefore, if we look at L being 0 to n, right, these give n plus 1 incongruent values of L squared. Mod P. And here P, of course, is still 2n plus 1 here. Likewise, m equals 0, 1, 2, n gives n plus 1 incongruent. Bad day. It's a bad day for spelling. Incongruent values of m squared mod p. Do we believe that? I mean, I believe that if we have proved that x squared is incongruent to y squared mod p. I think we've shown that. I don't think x can be congruent to y either. Basically, just because they're both from this list, right? I mean, we can just be a little bit more logical about this and a little bit less like technical. I mean, in other words, let's try to use our intuition here for just a second. We're taking two numbers between 0 and n. We're working mod 2n plus 1, right? So the equivalent representatives of things in here are pretty, they're not close to this. They're like way over here. So if I take, and I have equality of two things in here, if I have congruence, more to the point, if I have congruence of two things in there mod p, they have to be the same thing. But we're assuming that that's not the case, which is why this is vacuous. There is no solution to x congruent to y. It's reasonable no matter what travesty I have done with inequalities here. Okay, so once you have that, then that means that if you take values from here and you square them, right? They're distinct. For distinct inputs, right? You get distinct outputs, right? So how many inputs are there? N plus 1. As you square those, you get n plus 1 incongruent outputs for L squared and also for m squared, applying this result twice, all right? So then, likewise, you have n plus 1 incongruent values of minus m squared and minus 1 minus m squared, right? Putting a minus on it doesn't change the fact that they're still incongruent, and shifting by 1 doesn't change the fact that they're incongruent, right? I mean, we know that much about equivalence classes. We know that modular arithmetic, right? So this takes n plus 1 incongruent values mod p. All right, great. So who cares? All right. then what do you have is, if you think about L squared, and if you think about minus 1 minus m squared separately, how many values do we have? Well, n plus 1, right? How many values here? N plus 1, right? How many total values? Yeah, 2n plus 2 values, right? In the universe of equivalent classes of integers, or if you like, incongruent solutions, how many possible total incongruent solutions can you have mod p? P, right? Like mod 3, you get 0, you get 1, you get 2. That's it, right? Well, and they're equivalence classes, but so here, but p was 2n plus 1, right?
Pigeonhole.
Yeah, so essentially by pigeonhole principle, there has to be an overlap here. There has to be at least one incongruent class with two things in it, yes. So therefore, there exists what? Some x in the integers, right? Such that what? L squared is equal to x, which is equal to minus 1 minus m squared. Which then shows you what we really wanted to say, which is that, what? Oh no, I've lost my place again.
Should we say congruent to look at congruent classes?
Yeah, probably. But of course, L squared and minus 1 minus m squared must share some value for at least, mod p. Yeah, you're right. I should really. It's still the wrong thing to say. Still the wrong. I mean, I'm thinking of L. That is a stupid thing to write. It's a stupid thing to write. So sorry, guys. L and m are variables, right? There are variables which are indexing over this list 0 to n. This one's indexed over 0 to n, right? So the fact that they agree means that we can pick specific m and l such that, as Daniel was saying, L squared is congruent to minus 1 minus m squared mod p. Right? I was just trying to say this in a more complicated way by talking about the integer, which represents the class which they share, but that's kind of worthless. It's much more useful to say it this way, because then we can say what? M squared plus L squared plus 1 is congruent to 0 or 0, as my friend Deforming Sarkar would used to say. It was my great joy to ask Deforming to say back to me windshield wipers. He'd be like, shut up. Come on, say it. Fine. Windshield wipers. Like, say, you racist. Not a racist, I just thought we all right. And I did do some relativity. All right, so that's what we're trying to prove. See, because that's equivalent to saying that p divides 1 plus L squared plus m squared for some m and l. All right. That finally brings us to the four-square theorem. So here it is. Theorem for each n in n, there exists a, b, c, d in n and also 0 and 0, such that n equal to a squared plus b squared plus c squared plus d squared. So the proof, let's see, we already covered what? N equals to 1, 2, and, well, we even did 3, not that we didn't need to do 3. That's covered by the more general argument here. And we showed what? And we argued that, and we argued by 4 square identity. If we can prove this for odd primes, then we're done. I won't recreate the magic today. Just that's what we argued already. So where does this Lagrange lemma type argument come into play? So let me look at the argument. Maybe we can appreciate what in the world it is that I left out the other day. Finally penetrate my thick skull here. So if p divides, now why would we think about p dividing m squared plus l squared plus 1?
Those are all integers.
Say again?
Well, it's the sum of 3 squares, right?
Right.
So, 0, so it's the sum of 4 squares.
Oh, okay. So you're saying, did I say p was a? Oh yeah, I did say I'm an idiot. So p was odd here, wasn't it? Okay, so p is not prime. This definitely applies. Should we even use p was prime?
Yeah, for the
Oh,
congruence classes.
right here, right? That's where we use p was prime. For example, if you had, well, I guess it's odd. I don't know, when you're not working over a prime, if you have the product of things being 0, it could be the 0 divisors, right? That can't happen if p is prime. I don't remember him saying p was prime, but okay, let's get back here. Focus, focus. So consider m squared plus l squared plus 1. That can be rewritten as what? Check it out. This is the same as 1 minus li minus mj, and 1 plus li plus mj. Right. That's just algebra. But then what? If p divides m squared plus l squared plus 1, and we know it does if p is not prime, right? Then what? Well, p divides 1 minus li minus mj, or p divides 1 plus li plus mj, right? By the real prime divisor property we proved earlier today, right? Okay. Now, but that would assume what? There's actually more than I'm assuming here. What did we have in order to prove that? It wasn't just that p was a real prime. It was also that p was a Hurwitz prime. So it was a Hurwitz prime, which was also a real value, right? So suppose p is a real Hurwitz prime. That's where the weakest prime divisor property held. But now, by this Lagrange type lemma, we also have that if P divides this, it has to divide this or that. Okay. And then what? But my next argument. But P divides 1 plus or minus Li plus or minus Mj would imply what? Yeah, there's probably other ways of arguing this. Are you thinking in terms of the x plus I, x minus I homework problem we recently had? Ah, okay. I have a slightly different argument here. Let me follow it, and then I will think about yours. So your 1, I mean, I'm just doing correctly. 1 plus or minus Li plus or minus Mj is equal to gamma p for some gamma in the Hurwitz primes, right? In the Hurwitz integers, right? Which implies what then? That 1 plus or minus Li plus or minus Mj. This is a pretty direct calculational argument I'm giving here. I'm just dividing both sides by p, which I can do. P is real prime, right? No ambiguity or anything. But p is odd, right? Hurwitz integers are built from half-integer fractions, right? This is not a Hurwitz integer, right? And that implies that gamma is not an element of HC, right? Which, of course, is a beloved contradiction. Which means what? What does that mean? We've seen a necessary consequence of assuming that we have a real prime, which is also a Hurwitz prime, forces us to say that that number is both not a Hurwitz integer and a Hurwitz integer, right? That is the poisonous fruit of this illogical tree. By contradiction, this right here is the impossible. Therefore, by contradiction, there does not exist a Hurwitz prime which is an ordinary prime. And if you think back to last lecture, that was the linchpin that was missing, right? That was the one thing we didn't have that I said we'd have to prove. That was it. So if you put this together with what we talked about last time, you have a complete proof of the four-square theorem. This is something that Euler couldn't prove. If your head hurts a little bit right now, don't feel bad. Let me repeat what I just said. This is something Euler couldn't prove. The fact that we can appreciate and understand a proof of it with just like an hour and a half of our life is pretty significant, I think. And it's a testament to the work of people who followed him, right? Like, of course, Lagrange. And then later, the people in the 19th century who cleaned up these ideas, like Hurwitz, obviously. You see, Lagrange, right? You could somehow do all these arguments without using the algebra that was making our argument so simple, right? So whatever Lagrange did, he must have done just with integers. And the observation that, a prime has to divide this quadratic form. I think it would be much harder to read what Lagrange did as opposed to what we've done. So, again, another example of how abstraction allows you to solve a problem that it would have taken a genius to solve before the abstraction. Okay? I mean, Euler was a genius. I'm not. So. So that's the heart and soul of chapter 8. there's a discussion at the end, which is really interesting. I want to share some of these things with you. And so, you know, the two-square identity, there's something more to it. Like, what does it mean geometrically, right? What does the two-square identity mean geometrically? Let's go back to that. I have tried to uncover the geometric meaning to the four-square identity. He alludes to it in the end conclusion of chapter 8, right? But I will tell you, I have not been able to come to a clear understanding of that, so I won't even try, but I did figure out how quaternions represent rotations in 3 dimensions. I might share that with you here. I choose my word wisely. So the two-square identity, I mean, this is kind of the, we've learned a lot about the two-square identity. Now here's the geometry of it. So if you have 2 triangles, all right, suppose this is angle theta 1, this is angle theta 2. You've got A1, B1, A2, B2. You've got hypotenuse 1, hypotenuse 2, let's say. Then the two-square identity says that there's another triangle that you can construct over here, also with integer sides, where the hypotenuse is the product of the hypotenuse. The angle of the new triangle, by the way, is the sum of the angles of the old triangle. And the other one is, I don't know, just a second. A1 plus IB1. See, I'm confused. Yeah. Of course, this is what? This is A1, A2 minus B1, B2 plus I times A1, B2 plus B1, A2. Okay, so anyway, this is the A1, A2 minus B1, B2 is the side length. And over here you have A1, B2 plus B1, A2. Geometrically, that's what's going on with the two-square identity, is you can take these two, if you have 2 triangles with integer sides and integer hypotenuse, right? H1 and H2, and if H1, A1, B1, A2, B2, and I mean, well, I guess once you have A1 and B1 are integers, it then follows that the, no, it doesn't. Excuse me, what I'm talking about. If you have Pythagorean triples, right? A1, B1, H1, A2, B2, H2, then it follows that you also have this Pythagorean triple. But this is explicitly what it means in terms of the geometric content. You can take these 2 triangles with integer sides and construct a new triangle with integer sides. And the angle of the new triangle is just the sum of the angles of the old triangles. That is really easy to see if you look at it in terms of the so-called, I mean this, if you look at this in terms of like H1, e to the I theta 1, H2, e to the I theta 2. If you use the so-called polar coordinate representation of complex numbers, it's really easy to see this. This is H1, H2, e to the I theta 1 plus theta 2, right? So there you go. Here's the new hypotenuse. Here are the old hypotenuse. And here's, so the real part is the adjacent side to the angle. The imaginary part is the opposite side to the angle. And this is the geometric underpinning of the two-square identity. There is a similar comment that can be made for the four-square identity. That one I don't understand yet. And he also mentions lots of interesting things about, having these Eisenstein integers or the Gaussian integers, all these different number systems that we've looked at. each one of them comes paired with a very specific geometric thing you can do to either the plane or four-dimensional space or something, that they're associated with these regular patterns that you can fit into the plane or four-dimensional space, so-called pilings, right? I thought that was interesting. Let me share this with you, and then I will shut up for today. It shouldn't take me too long. So then next week we'll